Good afternoon. And now we're going to change the mood a little bit. We're going more to an experimental work. First, I want to thank the organizers for the invitation and for making this gathering possible in this hard times worldwide. I'll be presenting about the synthesis and magneto-optical studies of novel nickel-zinc ferrite zinc cobalt oxide nanocomposite as a candidate for photocatalytic applications. I'm presenting Beirut Arab University. These are some numbers about our university and campuses. An outline of the talk. First, I will start with introducing nickel-zinc ferrite, structure, characteristics, and applications. Same for zinc cobalt oxide, and the choice of the nanocomposite. Then we will discuss the characterization of the nanocomposite, starting with the structural properties and the composition by using X-ray powder diffraction, high-resolution transmission electron microscopy, and X-ray photoelectron spectroscopy. Then we will discuss the optical properties, including photoluminescence and ultraviolet visible spectroscopy. And finally, we will be focusing on the magnetic properties by studying the magnetic hysteresis curves. So zinc cobalt oxide has a hexagonal word side structure of space group P63MC. It is characterized by being a wide direct band gap N-type semiconductor. It has a large excitation binding energy. It's non-toxic, inexpensive, abundant, and it's mechanically stable. For all these favorable characteristics, it has been utilized in several applications, including photocatalysis, spintronic devices, photovoltaic cells, battery electrodes, antimicrobial activities, and gas sensors. For nickel-zinc ferrite, it's known to be a cubic structure with space group FD3M. It's characterized by being or having high mechanical hardness. It's soft ferromagnetic with low coercivity. It has a high permeability and a high resistivity. And it has been utilized in various applications, including biomedical science, permanent magnets, high-frequency applications, telecommunications, memory storage devices, and recently as a biodiesel. Choice of the nanocomposite. So as I mentioned, nickel-zinc ferrite, one of its pros, it's ferromagnetic or magnetically recyclable. And this is very important in photocatalysis because we need to recover the photocatalyst by applying an external magnetic field. So this is the advantage of the ferrite. However, it has a high recombination rate of the photo-generated electrons and holes, which reduces its photocatalytic activity. For zinc cobalt oxide, it has high photocatalytic activity, but it's non-magnetic, so it's not practical for environmental applications. We aim by combining these two nanoparticles to form a nanocomposite which is magnetically recyclable enhanced photocatalyst. Concerning the preparation method, we followed the wet chemical co-precipitation method, which is a chemical technique which is based on nucleation and growth by controlling the pH and by performing heat treatments to obtain homogeneous nanoparticles with a narrow particle size distribution. We obtained 5 samples of the nanocomposites of general formula 1 minus X nickel-zinc ferrite with X zinc cobalt oxide, where X varies from 0.1 to 0.5 and it represents the weight fraction of the zinc cobalt oxide. Concerning the structural properties and composition, the X-ray powder diffraction spectra has proven the existence of both phases, zinc cobalt oxide and nickel zinc ferrite, without any traces of other impurities. The two theta values and the lattice spacing have shown no variation with the nanocomposite addition, which confirmed the stability of the phase and the absence of chemical interaction or substitution between the ionic species forming the nanocomposites. The transmission electron microscopic studies have confirmed the synthesis at the nanoscale, and the grain size diagrams, histograms, have confirmed the synthesis of nanophase in the size range from 27 to 34 nanometers. The high resolution transmission electron microscopic studies have shown different grays with different plane orientations, crystallographic plane orientations, assigning to the polycrystallinity of the samples, and the selected area electron diffraction patterns showed concentric circles from which the HKL indices were determined and were found compatible with those from the XRD studies. Rate-field refinement was employed for all XRD patterns, and the phase content was determined and was found matching the theoretical phase content. The lattice parameters were found fluctuating around values previously reported in previous literature. These fluctuations were assigned to the microstrain induced on the lattice due to the addition of the zinc cobalt oxide. The grain size and the crystallite size obtained from XRD and TEM were also found comparable. In order to detect the elemental composition of all samples, X-ray photoelectron spectroscopy was performed. All samples have shown the presence of all elements, and a deconvolution of the spectral line of zinc, cobalt, iron, and nickel was done in order to determine the oxidation states of the elements. Zinc was found in an oxidation state of +2. Nickel was found in a mixed valency of +2 and +3, and cobalt as a valency of +2, and a valency of +3 was assigned to Fe in both octahedral and tetrahedral sites. The optical properties, starting with the ultraviolet visible spectroscopy, the absorption curves for all samples were shown, and the famous stock plots were employed in order to determine the band gap energy of all samples. Now, in nanocomposites, introducing two nanophases together causes a distortion in the band structure of the nanocomposites. So this is why it's interesting to study this distortion by doing the Urbach analysis. So we show the logarithmic plot of the absorption coefficient versus the energy. And from these plots, we can determine the Urbach energy, which is an indication of the degree of distortion in the band structure. As shown in the graph here, we show the graph, the variation of the band gap energy in red and the Urbach energy in blue and the grain size in black. There is an inverse relationship between the band gap energy and the other two variables, suggesting that the variation of our band gap energy is due to the quantum size confinement effect due to the variation of the size, and also due to distortion in the band structure due to the variation of the Urbach energy. The photoluminescent studies, which are very important in photocatalytic activity, were performed also. As we can see, we have a violet near band gap emission, and we have deep level emissions for all samples. We also found a decrease in the intensity of the main peak, and this decrease is favorable for photocatalytic activity because, as you know, intensity is inversely proportional to the rate of recombination of electron and hole pairs. We performed the convolution of the PL spectrum of the sample with x equal to 0.5 of the nanocomposite, and the blue emissions were assigned to the zinc interstitials and the Zn2 plus transitions in tetrahedral sites. The blue emissions were assigned to the nickel 2 plus transition in octahedral site. The green emissions were assigned to the oxygen vacancies that causes distortion at the level of the oxygen metal bonds. And the red emissions were assigned to the Fe3 plus transitions in octahedral sites. Again, the chromaticity coordinates were determined from the spectral power distribution of all samples. And the color coordinates showed a shift from the blue region to the violet region, and this is favorable for photocatalytic applications because it means that there is possibility of harvesting a larger amount of the visible spectrum. Finally, we'll discuss the magnetic properties. For nickel zinc ferrite, room temperature hysteresis curves have shown a soft ferromagnetic behavior. This behavior was explained based on the sublattice Nilf model, which assumed a super exchange interactions between Fe3 plus in both octahedral and tetrahedral sites. For zinc cobalt oxide, the hysteresis loop was deconvoluted into two portions: a diamagnetic portion, which was attributed to surface and legend effects, and a soft ferromagnetic part, which was explained on the basis of the bound magnetic polarance theory, which assumes a ferromagnetic coupling between the oxygen vacancies and the 3d zero electrons and the CO2 plus ions. As for the nanocomposites, all samples have shown a soft ferromagnetic behavior. The value of the saturation magnetization was obtained from the extrapolation of the M versus 1 over H squared curve. And as you can see, MS showed a decrease by 50%. But even though we have this decrease, it's still ferromagnetic and it's still practical for photocatalytic applications. So we didn't lose the advantage of having a ferromagnetic zinc ferrite. Several magnetic properties were also determined, including the saturation, magnetization, and the remnants. They both showed a decrease. The coercivity fluctuated around 50 Oersted, and this was expected because we don't have variations in strong fluctuations in the grain size or impurities or surface defects. The squareness ratio was much less than 0.5, which infers that we have spin canting effect in a large number of the grains of the nanocomposites. And the magneton number has also showed a decrease compatible with the variation of MS. And the effective anisotropy field anisotropy constant has also shown a decrease with the increase in the amount of the added zinc cobalt oxide in the nanocomposite. Finally, in order to go deeper in the nature of exchange coupling between two nanophases, we plotted the Henkel plots to investigate the nature of the coupling interactions. And as you can see, for nickel, zinc, ferrite, and all nanocomposites, the Henkel plots had showed a positive delta M, which means that the presence of exchange coupling interactions. For zinc cobalt oxide, for higher field, the delta M showed a negative value, which indicates dipolar interactions. Finally, switching field distribution was done for all samples by plotting the dm by dh versus h curves. All samples have shown a single peak, confirming the presence of a single magnetic phase, and as you can see, with the amount of the nanocomposite of zinc cobalt oxide increase, the full width of half maximum and the intensity decreases, again signifying the deterioration of the exchange coupling between the two phases. Conclusions. So, successful synthesis of both nanoparticles and nanocomposites was reported, and the grain size was found in the range of 27 to 35 nanometers. Oxidation state of all elements were determined by using XPS studies. Optical properties investigated using ultraviolet visible spectroscopy has shown the dependence of the GaN-BAP energy on both the crystallite size and the Auerbach energy. Photoluminescent studies have shown near-band edge emissions and deep-level emissions with a remarkable decrease in the intensity of the PL spectrum with the sample for X equal to 0.5, suggesting an enhancement of the photocatalytic activity of the nanocomposites. VSM studies have revealed soft ferromagnetic nature of the nanocomposites. The saturation, magnetization, and isotropic field were reduced with the increase of X. Henkel plots suggested the dominance of the exchange coupling interactions among these nanophases, and the dm by the dh plots verified the presence of a single magnetic phase. Finally, these enhanced optical properties, in addition to the variations of the magnetic properties, suggest the use of the novel nanocomposite as a candidate in magnetically recyclable photocatalysts. This work was recently published in Ceramics International. And concerning the future work, we're now working on investigation the effect of cationic distribution on the magnetic properties by using Raman and MOS power spectroscopies. And we're investigating photocatalytic activity of the nanocomposite for water treatment regarding contamination via synthetic dyes and organic pollutants. Thank you.
That's a very interesting talk, very interesting work.
Thank you.
I would have several questions, but let me ask you first. When you do your XPS study, do you do ion thinning to take away surface contaminants from your samples, or you do it in the nano powders, for example?
Yes, we did for the nano powder, and we got some traces of carbon also, which was due to the contamination with air.
Right. Yes. But that sometimes it can be just from the handling. You have CO2 again, and you know, even when we work in high vacuum and we measure without taking out into the air, and we have done work with alloys and metals, and we still see carbon contaminants even without coming into the air. So just from the walls of the vacuum equipment. So this is we usually do this just to make sure that it's not the contaminants that are being adhered, and this is what we measure. But I guess when you have nano materials there, dispersed, it's quite difficult to do that.
Yes.
The other one is when you say you have optimum, you sort of reach an optimum spectral range, I guess, for photocatalytic activity coming towards the visible, right? And you would like the photocatalyst to work with sunlight if possible.
Yes, sure.
But I don't know. It looked like it had a maximum in the blue part of the spectrum. Is that correct? Or?
Yes, the maximum was mostly a near band gap edge emission, which is in the violet region. But as you see from the chromaticity diagram, there was a shift in the color coordinates, which mean that we can harvest a larger amount of the visible spectrum. Yes.
And how how is the composite really prepared? Does it have? Is it just mixed, or do you need to go to?
Yes, it's mixed and it's subjected to further heat treatment after mixing the 2 nanophases.
And up to what temperature is it?
840 degrees.
840.
Yes.
Because do you suspect that you could have cobalt ferrite synthesis, in the grain joints between you observe necking or any of these phenomena when you
yes, actually, it was like we tried to look for the impurities using the XRD, but we didn't detect. This is why we're trying now to do the Raman spectroscopy, because it's more sensitive. And this is why the anisotropy parameters, concerning the discussion of these parameters, because they're very sensitive to impurities, we left it for further investigation after studying this cationic distribution and from the Raman spectroscopy.
Very nice. Thank you very much. Very, very nice one.
I would like just to ask you about high resolution TM. This was done in Lebanon?
Sorry, no, this was done actually in Egypt. Yes, we are collaborating with a lab in Egypt, in Alexandria.
With
Yes.
Alexandria?
Yes.
Okay. And, okay. So it's okay. It was more clear for other details. We thank once again the speaker.